Hi, we're going to look at sections 2.5 and 2.7 from chapter 2. So first we're going to briefly talk about electron structure. So we previously have talked about the whole structure of the atom, right? The periodic table, main group elements, and like what structure of the atom, like what's inside of it. So protons and neutrons. Now we're going to talk about the electron structure for just a second. Electrons are particularly around the outside of the atom. They're not in the nucleus, and we call this the electron cloud. These regions are kind of split into general areas. We call these principal energy levels or shells. So think about kind of like maybe the Bohr model that you might have seen in physical science classes, where we have like energy level 1 around the nucleus. If this is the nucleus is here in the center, energy level 2 around the nucleus, energy level 3 around the nucleus, and so forth and so on. So the lower the energy level, the closer they are to the nucleus, and that's actually the lower the energy. So think about it like stairs. If you're trying to go up one flight of stairs, it doesn't take as much energy to go up to 3 flights of stairs. And we call these the energy levels or shells. It's not exactly that electrons move around in orbit, kind of like the planets do around the sun. Electrons are a little more wild than that. They actually hang around in these little clouds that are like uh, different shapes. So we'll talk about those shapes in a second. The larger numbers are farther away from the nucleus and they can hold more electrons. And so the first energy level can only hold 2 electrons. The second energy level can hold a max of 8. And then we go up depending on how many shells we have. So the formula is 2n squared, where n is the shell number, and you don't really have to know more than 4. Here, you won't be asked questions like, hey, how many can like on an exam, you won't be asked a question like, hey, how many electrons can the fourth energy hold? I'm just trying to give you a general idea of what the electrons look like. So we have a small number in the first energy level, and then as we increase the energy level, get farther away from the nucleus, we can actually add more electrons in because there's more space out that way. Those energy levels are then divided into subshells, and we identify these with letters S, P, D, and F. These are orbitals. These are like these areas I was talking about, these spatial areas, kind of cloud shapes where the electrons exist. Probably. So the probability of finding an electron is high in this area. It's kind of like a heat map of like where you might find an electron. And these subshells have different numbers of orbitals inside of them. And you don't have to memorize any of this. I'm just giving you this information. So if you do see it at some point in the future, you're familiar with, oh, we're talking about the areas in which electrons could possibly or probably be found in each of those energy levels. So in the first shell, we would have a 1s orbital, and you could fit 2 electrons in it. In the second shell, we would have a 2s orbital, we can fit 2 electrons, and then we would have 3 2p orbitals. Each of these orbitals would fit 2 electrons, so we have 6. That's where we get the number 8 from. So this is just how we get these numbers. You're not going to be asked for specifics on this, but I do want you to know that if you do see something that has 1s, 2s, 2p, 4d, like if you're seeing these things, it's all talking about kind of where the electrons are in the atom. We're not going to be doing electron configurations in this class, but you may see it at some point. You may never see it again, but I just want you to know that if you do see that at any point where your maybe 1152 instructor is talking about 2s electron or something like that, that's what they're talking about. So S and P, they're only ones we're really going to look at. S is basically an S orbital. It's just like a spherical shape. So it's like a cloud. This is a probability map of where we would find an electron in an S orbital. These are lower in energy. The P orbitals have dumbbell shapes. There's 3 of them. There's one in the X direction, one in the Y direction, and then one in the Z direction. And Z is kind of like 3D coming out at you. And then there's 3 of these P orbitals. And so kind of together, they look like this. And they get more complicated as we go into D and F. But basically, these are saying, like, if you are a 2p electron, that means that you're found in the second energy level away from the nucleus, and you're probably found in one of these three shapes, these kind of three areas around the nucleus. What we're really going to focus on are the valence electrons. And so valence electrons are really important for moving forward in what we're going to do. And so we're just going to kind of hone in on valence electrons. But again, you kind of have to understand a little bit about what we're looking at to get the valence. So the chemical properties and really depend on how they bond, how things come together, depend on the valence shell. So the valence shell is the outermost shell, the highest value of N. What we're looking at here, these are electron configurations. We're not going to worry about deciphering them. We're not going to worry about writing them, but I do want you to be able to pick out the valence shell. And I'll show you a trick to where you don't have to use these to tell the valence. That's probably what most of you are going to use anyway. But if we look at the big numbers in front, those are our energy levels in the electron configuration. Then you have the letters that tells you what shape, kind of what orbital it's in, and then the small numbers at the top, the subscripts, tell you how many electrons are in that energy level in that shape. And so we're going to look for the highest energy level, which is the big number. So for this one, the highest energy level is 2, and there are 2 electrons in that. So we say 2 valence electrons because there are 2 in the highest energy level. For this one, we have energy levels 1, 2, and 3. And the 3 is the highest energy level. So let's count up all the electrons we see in energy level 3. Well, there are 2 in the 3s, and there are 5 and 3p. So we add those together to get a valence of 7. So that's really what valence means when you look at it, an electron configuration. You say, all right, how many are on the very outside? And it's the outside electrons that tell you all the chemical properties because they're the ones that interact with other elements and other atoms. So electrons in the same group have similar electron configurations. Remember, groups are the columns. Groups are the columns on the periodic table. They have similar electron configurations because they have the same number of valence electrons. So everybody in one column will have the same number of valence electrons all the way down. This happens for the main group elements, so the tall columns, not the short columns. Exception of He only has 2 valence electrons. Everybody else in its group has 8. And the chemical properties are very similar because their valence electrons are similar. So if everybody has a certain number of valence electrons on the outside, they'll behave very similarly. So we call them families sometimes because they do behave in similar ways. So as you go across the periodic table, really we can split our tall columns up in 8 pieces. This is either 1A through 8A or 1 to 13, 14, 15, 16, 17, or 18, depending on what periodic table you're looking at. Everybody in group 1 or 1A has 1 valence electron. Everybody in group 2 or 2A has 2 valence electrons. Then we skip the valley because those are a little bit strange as far as electron configurations go. Then everybody in group 3A or group 13 has 2 plus 1, 3 valence electrons. And so the valence electrons across the periodic table go 1, 2, 3, 4, 5, 6, 7, and 8, with the exception of helium only has 2. Because it only has 2 electrons total, it can't have 8. And so as you move across the tall, this is the tall groups only, just count 1 through 8 across, and then I'll tell you the valence electrons for everybody in that column. So you don't have to know the electron configurations. You don't have to know this 2s, 2p kind of stuff. You just have to know, can I count 1 through 8 on those tall columns later when we ask how many valence are in a thing. When we know the valence electrons, we can say that out loud. We can say, hey, this has this many valence electrons, but sometimes we want to be able to write out very quickly how many valence electrons are around a singular atom or an element. So we use dots to represent electrons, and valence electrons will represent as these dots around the element symbol. So we're not talking about all the electrons in the atom. We're talking about only the valence. Each dot represents 1 electron. we have single dots that we use first, and then we pair them up. And so what we kind of think about doing is if we have hydrogen, for example, it has one valence. So we put one dot, and you can really put that dot anywhere. You can put it on the top, the left, the bottom. It doesn't matter. Just think about the element symbol as being a box, and you're going to put a dot on one of the sides. If I have 4 dots, for example, I'll put one on each side of this box around the chemical symbol. For example, carbon has 4 valence, so I put 1, 2, 3, 4. I don't pair them up like it wouldn't be 2 on one side and 2 on the other side. We're going to separate them because electrons repel each other, and so they'd rather be single first before they pair up. And so we match that quality when we're doing depictions of them. But for example, with oxygen, we would probably start with 1, 2, 3, 4, and then we would go 5, 6. And you could go 5, 6 on any of them. You could have oxygen look like this, or it could look like that. It doesn't matter as long as you've got 2 unpaired and 2 pairs to make up your 6. And then for your halogens and in group 7, the valence electrons, you're going to have at least just one unpaired electron. Everybody else is paired. And so you can see as you go down, you can kind of think about, well, what would lithium be? Lithium is 2, so we put 1, 2. What would boron be? It's 3, 1, 2, 3. What would nitrogen be? It's 5, 1, 2, 3, 4, 5. And etc. These don't have to be that difficult. And again, you're talking about multiple choice quizzes and exams here, so you're really just looking for like which one is correct or which one is incorrect in an example there. In ALEKS, you may actually have to put in the dots. And then lastly for this chapter, we'll talk about periodic trends briefly. Periodic trends are important because they kind of help us figure out what properties and what things are going to happen with things. And so as we go down the periodic table, we're going to increase in size. And this actually should make sense because as we go down the periodic table, actually, we add rings. So remember we talked about how those energy levels increase as we go out away from the nucleus. Well, as we go down the periodic table, we increase the number of rings or number of energy levels around the atom. So to think about for atomic size, think about building a snowman. We build a snowman by putting the biggest one on the bottom and the smallest one on the top. And so the trend as we go down the column, the valence electrons get farther and farther away from the nucleus, and this affects how easy it is to remove them and how easy it is to change them. So the farther away you are from the nucleus, the easier it is to take those electrons away. If I have my electron way over here, my nucleus is right here, it's a little bit harder. The nucleus doesn't have a hold, a pull on those electrons as much. Versus if my electron is here, my nucleus is in the middle of a very small atom, the nucleus has a really strong hold on the electron. Remember that opposite charges attract. Your nucleus is positive and your electrons are negative. So the farther away those two particles, the easier it is to remove the outer particle. So that's why we talk about these trends. So they can kind of tell us a little bit about how iodine might act differently than fluorine in a chemical reaction. So or in bonding. So as we go down, we're increasing in size. Think about building a snowman. Now, as we go across the periodic table, you may think that because we're adding protons and we're adding electrons, that the size gets bigger. But actually, as we add protons, the pull of those protons is more intense. And so it's going to pull the electrons in tighter. So a quick way to think about this is to knock over your snowman. So we built a snowman and then we knocked it over. So as we go across the periodic table from left to right, we decrease in size. Oops. So down the periodic table, build a snowman, increase in size as you go down. Across the periodic table, knock the snowman over, decrease in size as you go across. And so as we go up from bottom left to top right, we decrease size. In general, up and to the right is decreased in size. Let me redo all of that, make it a little more clear. So this is decrease in size. So the biggest is going to be francium. Well, the biggest in this trend and the biggest for real is francium. The smallest in this trend, we don't really include noble gases in our trend. I mean, you can include noble gases in your trends, but hydrogen is actually the smallest, and so that's a little bit of a difference. But then you would have the smallest being the top right corner. I like to use fluorine as a guide because it's also F. So I'm not going to put smallest because it's not the smallest, but I'll put smaller. So if you can remember either the snowman, building the snowman, knocking him over, or you can remember FR is the biggest and F is the smaller, not the smallest, but smaller, and you can figure out what your trend is based on those two Fs. So pick a way to think about how you want to remember that and, go with that thing. And then we kind of talked about this a little bit already, but I didn't give a name to it. Ionization energy is how much energy do you need to remove an outer electron from an atom? And so when we're thinking about how do we remove an outer electron from an atom, we have to think about how tightly is the nucleus, are those protons holding on? Like I said before, if you're very close, so if your nucleus is here and your electron is here, the distance between them is very close, and it's going to be harder to remove that electron. So that would have higher ionization energy. If your proton is here and your electron is way over here, the distance is a lot greater, and it'll be easier to remove that electron because it's so far away from the thing it's being attracted to. Think about two magnets. Two magnets that are actually touching or really close together, harder to separate. Two magnets that are farther apart, easy to separate. So as far as trends go, we decrease as we go down the group. Because if you get bigger, it's easier to remove. So bigger size, easier to remove the outer electron. So that's lower ionization energy. So we'll call ionization energy IE. And then we can kind of apply that here. So as you go across, you get smaller. So smaller size, harder to remove the electron. This would be larger ionization energy. So again, I like to pull out my francium. Francium has lowest ionization energy. And then fluorine, again, fluorine doesn't have the highest of all the elements because you've got the noble gases and stuff to the right, but a lot of times the noble gases don't really participate in bonding and stuff, so we don't really consider their periodic trends too much. Yes, you can talk about their size, and you can talk about their ionization energies, but they really don't do bonding and things with them, so we don't have opportunities to really use that information as much. But with fluorine, you definitely do. So I like to think about the two Fs, francium and fluorine, as kind of opposites. So we'll put here as high. It technically is a very, very high ionization energy. I think it's probably higher for a noble gas, but we can say kind of highest, kind of. So we'll just say higher ionization energy. You can think about it as the highest just for purposes of this class if you want to. Okay, and so that's it for this chapter. If you have questions, let me know.